Hello friends. So today we are going to find out the coefficient of interface friction, and we have a problem based on pull out test data. So in continuation of the previous video, there is going to be the example numericals based on the pull out test data. The length of the reinforcement strip is given to you as 0.3 meter. So here in the given problem, you have been given here the length of the reinforcement is given to you as 0.3 meter. And the width of the reinforcing strip is also given to you as 29 mm. So the width of the reinforcing element BR is given in this problem as 0.029 meter. And effective stress on the strip is given to you. So the vertical stress is 180 kilopascal, and the maximum pull-out resistance, that is T maximum, is given as 1.078 kilonewton. So that's also given. And we have to find out the coefficient of apparent friction. So this we need to find it out from the pull-out test. And the reinforcing strip is bamboo. So length of the bamboo strip is given to you. The width of the reinforcing strip, that is bamboo, is given to you. And the maximum pull-out force when the vertical effective stress is going to be 180 kilopascal. The maximum pull-out force, T max, is given in this problem. So we need to find out the coefficient of apparent friction. So the coefficient of apparent friction, as you have seen in previous video, is given by maximum pull-out force, and the maximum pull-out force is called T max upon 2 times the effective vertical stress multiplied by the length multiplied by BR. The expression which I have covered in my previous video, and you are all well aware of it. So from pull-out test data, if you substitute everything and calculate, you will be getting the coefficient of apparent friction Fs star. So let us substitute the values. Already it is 1.078 kilonewton T max divided by 2 into this effective vertical stress is given to us as 180 kilopascal. So into 180. The length of the strip is mentioned as 0.3, and the width of the reinforcement is given to us as 0.029. So if you calculate this, you will be getting the coefficient of friction. So let's calculate. So if we calculate 1.078 divided by this is 0.344. 0.344. So this is the answer of part 1. Now, if you look to the second part of this problem, if the surcharge of 60 kilopascal, so when you are going to carry out the pull-out test, you have a box here, and here is the reinforcement. You have a slit over here, hole, and this is the reinforcing element where you apply the pull-out force. So displacement, you record it for certain given displacement. You are going to record the pull-out force T, and from displacement versus T data, you can find out T maximum. So the effective pressure over the reinforcing strip was 180 kilopascal. Now what is happening in the second problem? The surcharge. So you are going to put the surcharge here, Q. So what is the value of surcharge? Q, it is 60 kilopascal. So in addition to the vertical pressure, the surcharge Q is 60 kilopascal, and therefore the uh, 60 kilopascal is additionally placed. Find the coefficient of apparent friction. So we will have to find out the coefficient of apparent friction will be given by T max divided by 2 into effective vertical pressure plus surcharge into L, length of the strip, into width of the strip. So this is the formula now. So there is a slight change here. The total vertical pressure over the reinforcing strip is going to be summation of the surcharge plus effective vertical stress. So now in this problem, second part of the problem, you will have to find out the coefficient of this. So the value of T here, if the surcharge of 60 kilopascal is additionally placed, we will have to find out the total pull-out force. We will just calculate it. And in this problem, the surcharge is additionally felt. Find F star if T max, the maximum pull-out force, if the maximum pull-out force T max equal to 1.437 kilonewton. So this is the second part of this problem. So how will you find it out? Already you have the information. This is the formula here. So now in place of T max, you place this value which is given in the data. So 1.437 kilonewton divided by 2 into 180 plus 60 multiplied by 0.3 into 0.029. So if you calculate this, let us calculate. There is going to be 0.344. So in this problem, you can see for the second part of the problem, the value of this one comes out to be 0.344. So the coefficient of apparent friction, this is the answer for part 2. So you have found out the coefficient of apparent friction for the given data. So this is how you can attempt this kind of problem that are expected in any competitive examination. Now this is the second problem based on soil reinforcement interface friction. Wherever there is going to be sliding of the soil mass over the reinforcement, for sliding test, what you do it is the modified box shear test. So in this problem, you have performed the modified box shear test and the data are given to you. The dry unit weight of sand, which is in the shear box of size 60 mm by 60 mm. So that is the cross-sectional area. The dry unit weight of sand is given to you as 16.5 kilonewton per cubic meter. And the reinforcing element is going to be aluminum sheet. So you know how to perform the modified box shear test, as I have already explained to you that this box will be divided into two parts, and this is going to be lower part is going to be wood, and here is the reinforcing element that is fixed to the lower part of the shear box, and upper part will be filled with sand, and then you apply the vertical normal stress, which is given over here. So what is the normal stress? It is 16, 28, 41, 66, 91. So it's increasing, and the corresponding, when you are going to shear it, when this is going to move like this, then you are going to have the interface friction, and the interface friction is called angle of wall friction, that is between this reinforcement and this sandy soil. So this is the sandy soil. So here the unit weight you have maintained, reinforcing element is aluminum sheet, and these are the data available to us. So at 16, what is the value of shear stress? You have measured with the proving ring, it is 0.8. At 28, it is 15. At 41, it is 18. At 66, it is 30. And at 91, it is 40. So how will you find out the angle of internal friction? The angle of wall friction, delta. So find delta, angle of wall friction, that is the friction between the aluminum sheet and the sandy soil. So a simple problem can be done very easily. Let us see how we are going to do it. So what we have to do it graphically, we can solve it by taking a graph paper, and it is going to be the normal stress on the x-axis and the shear stress tau in kilopascal, and this will be in kilopascal. Take a simple graph paper, and the reading for normal is from 16. So maximum value is 90. Let's say this is 10. This becomes 20, 30, 40, 50, 60, 70, and so on. We can proceed further. 10, 20, 30, 40, 50, 60, 70, then 80 and 90. So this is 0, 10, 20. This becomes 90, 30, 40, 50, 60, 70, 90. Here, shear is going to be maximum 40. So this is going to be 10, 20, 30, and 40. So sigma n in kilopascal on the x-axis, right? And on the y-axis, you have plotted tau, shear stress. So when the value is 16, the corresponding value of tau, this is tau, this is sigma n. So what is the corresponding value of tau is 8. So at 16, so it is going to be somewhere here. So 1 point you have got it. Then next value is 28. So this is somewhere here, 28. You can, actual value you will be getting when you take a graph paper. And this is going to be 15. That means this is the midpoint. And the second point, right? Then if you are going to 41, 30, 40, 41, very near to this, 41, then what is the value? It is only 18. So 18 means somewhere here. Okay. Then when it is 66, 30, 40, 50, 60 is 60. So 66 means somewhere here. What is the value here? It is 30. 30 means this is the another value. You are getting it. And when it is 91, it is 40. So when it is 91, it is going to be 40. So you can draw a smooth line. These were the points. 1, 2, 3, 4, and 5. And the inclination of this line will give you the value of angle of wall friction, which is to be calculated. So this we can find out. Therefore, from this plot, find out the value of delta. So delta will be this divided by this intercept. So it is at 90. You can find out what is this intercept and this intercept. So tau, so tan delta, delta will be tan inverse tau divided by sigma n. From this, you can find out. And this comes out to be approximately 25 degrees. So this is the answer. So problem number 2, we could solve it very easily by taking a graph paper, plotting it, and from the plot, we get this value approximately 25 degrees. So that's the answer. So friends, with these two problems, you are exposed to the nature of problems, how you carry out the test in the laboratory, whether you carry out pull-out test or you carry out modified box shear test, you can find out the interface friction. So our aim was to expose you to calculate the interface friction. So you have seen from pull-out test data, the maximum pull-out force T max is found out at certain displacement. What is the pull-out force? That you will have to find it out. And T max divided by 2 times sigma V plus Q, where Q is the surcharge, into length of the reinforcing element, which you are pulling, multiplied by width of the reinforcing element. And that gives you the apparent coefficient of friction. But if it is a sliding of the particle, as I have explained in the previous video, you need to carry out modified box shear test data, and these were the data. And how simply by plotting the given data, sigma n on the x-axis and tau, which is the shear stress, on the y-axis, we are in a position to calculate the value of delta. So with this, I come to the end of this soil reinforcement interface friction. In the next video, I will come out with geosynthetic applications in RE walls, that is reinforced earth wall. You know that RE walls are very, very popular. And because it is flexible walls, particularly in seismic zone, the RE walls are quite popular. And how to design it? The internal stability as well as external stability, you will have to check it. So what are those design concepts? That will come up in our next video. Thank you very much.